So today is the fourth class of group theory. Do you guys have any questions that we can start with first?
Sir, can you briefly explain the Coset space?
Right, sure. So Coset space to understand Coset space, you first need to understand what a coset is, right? So if you have a group G and H is some subgroup, then we can partition the group, partition the set, that is the group, into disjoint subsets. And these subsets would be the subgroup H itself, then say G1 H, another coset, G2 H, dot, 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 say GK minus 1 H. So there are K cosets. Okay, so if I look at a pictorial representation of this, this is our group, and so this is G, and the coset construction divides it into little bits. This is a subgroup, but the other ones are not subgroup, but they're sets. Okay?
Yes,
so,
sir.
okay. So the idea here is that the partition is in terms of disjoint subset. Okay, there is no overlap. So that means now we can construct a new set. And this new set is usually referred to by G over H. And this set consists of all these individual subsets. So we know that when we are doing set theory, that we can have sets of sets, right? So G over H is a set of sets where each element is a coset. Is that clear, Josh?
Yes, sir.
So now this new set G over H, this set is called a coset space. So it is the space of all the cosets. It's the space of all the cosets under H. Okay? So the coset space is in general not a group. Okay, the coset space G over H in general is not a group. But if H is a normal subgroup, what does H being normal subgroup means? It means that if you conjugate an element, well, if you do this action, so meaning that if you take an element from H and take some G and G inverse, then if you get H prime, which is also in big H, if this is true for all H in H, then we can say that G of H is equal to, say, H prime of G, right? So then we call H a normal subgroup. Okay? This need not be the case for all subgroups. If H is a normal subgroup, then we can introduce a group multiplication, a very natural group multiplication, where we take two cosets, say G1H and say G2H, and define the multiplication between them as being the coset that results from G1, G2 of H, okay? And you can verify, and I think this is one of the exercises I gave, that, this construction, does make G over H into a group, and that group is called the quotient group. Okay, so this is the coset group or the quotient group. And as an example, we can take the group of all real numbers under addition, and the integers form a normal subgroup of the real numbers, and therefore, we have, we can form a quotient group out of that, right? So we can have R over Z. Okay, so, and the other comment I think is relevant for this is that if G is abelian, meaning that all its elements G1 and G2 commute, then any subgroup H is automatically normal, because if I have G inverse, because G is abelian, that means that this is equal to G inverse of H, which is H, which satisfies the condition that H is normal. So if you have G abelian, then it's it's a normal subgroup. Any subgroup is normal, and therefore there's an automatic way of constructing a coset group. Okay.
So
Yes.
I have a question. So
Yeah.
the coset, you said disjoint coset. So wouldn't they make space even if they are not disjoint, even if they have overlapping elements?
Well, the cosets do not overlap because it's an equivalence relationship, and equivalence relationship will always divide a set into disjoint subsets.
Also, it's by definition.
Yeah.
Oh, okay, got it.
Like, that's another thing I wanted you to, I think, verify. It wasn't an exercise, but I wanted you to convince yourself that when you have a equivalence relationship, and you on a set, that equivalence relationship divides that set into disjoint subsets. Okay. Okay, I think there's a comment. Let's see what the comment is. Okay, so it's about the sound. Okay, any other questions or comments? So you might ask, okay, what is this group? right? So I leave that as an exercise. It's an interesting group. And it's a group that we will very often sort of, come across. So, I mean, think of it geometrically. So the real line is like this. It's a non-compact set. And the integers are a subset. This is, of course, like, I am cheating a little bit because all the definitions I gave you were for finite groups, assuming finite groups, and then I tell you about an example where both the group and its subgroup are infinite, right? So I'm surprised that no one has caught me out yet, but the idea is that, these ideas spill over to the infinite group. I just used the finite setting to define them, because then, I can draw pictures like this. I can draw pictures like this and build up intuition. But this also works if, these things, go all the way to infinity in all directions. And it also works for continuous groups, as we shall see. Okay, so R is a continuous group, whereas this guy is a discrete group. They're both infinite. So when you do the quotienting of R over Z, what you're doing is that you're identifying these points, right? You're essentially identifying all these points. And you're identifying any point that is shifted by this amount. So, you're also identifying this point with this point, and this point, and this point. So can someone tell me, I don't want to, it's a circle, exactly. So it'll look like a circle. So you immediately know that the circle is going to be some sort of a group. Now, the exercise I want to give you, and it's a fun exercise, so it's not going to be a blue exercise. So, but I would recommend that you do it. It's very highly recommended. Is that find the group operation on the circle. Okay. So, so you are actually kind of discovering a new group, very interesting group that has lots of applications in physics, as well as mathematics. Okay, so that's kind of our review of
Sir,
the
I have a
quotient.
question.
Yes.
So how do we say that it's a circle? So I wasn't quite clear with.
Topologically, what does it look like?
Well, there are many identifications. So if there was just one identification, I would have concluded that.
No, I mean, you are saying that, when I go from here, when I go from, say, here to here, I end up here again, right? That's basically what this identification is doing. Think about it for a minute, and
Is it like a circle with many windings, for example?
No, it's just a circle.
Okay.
It's a line with, where you have kind of, so this red point is mapped, all the red points map to one red point here, okay? All the blue points map to, say, a blue point here. And suppose that, so on and so forth. You have, in the middle, you have some pink points. Okay, and the pink point, all the pink points would map here, right? So thinking about it in that way, you can convince yourself that this is going to be a circle. Okay. Okay, any more questions? Okay, we have Otton is saying there is an isomorphism between R Z to S1 at Nahi. Okay, well, that's basically what we're doing here, right? Yeah. All right, so, but I want you to discover the group multiplication for this new group. Okay.